the chain rule. This is an extremely important rule for finding derivatives. Let's look at this function. If we have 5x plus 4 quantity squared and we wanted to find the derivative, our best bet would be to take this function and multiply it, so that instead of expressing it as the quantity squared, we would write 5x plus 4, 5x plus 4, multiply those together, get 25x squared plus 20x twice, so 40x plus 16. Now we would have a polynomial and it would be easy for us to find the derivative. We've got power out in front multiplied by the 25 is 50. X to the first as we decrease the power by 1 plus the derivative here would be 40. So not hard to do if we just multiply that out, turn that into a polynomial, and then take the derivative. However, what if our function was 5x plus 4, the quantity to the 100th power? It is certainly not going to be practical to multiply this out and have a polynomial of degree 100. So instead we are going to come up with a rule for finding derivatives when we have a composition of functions, so a function within a function. As we look at our original function up here, I basically have a function squared, and the function that is squared I'm going to call u. So u is this function inside of a squared function, and it is 5x plus 4. And then our outside function is just simply the stuff inside squared, and our stuff inside 5x plus 4 we called u, so we could express this as a function of u and write it as u squared. So we're going to come up with a rule when we have this composition of functions inside of functions, for finding the derivative. And first of all, we're going to just start with the derivative and look at our Leibniz definition for derivative. We have the limit as delta x approaches 0 of the change in y over the change in x. And we could express that also multiplying by delta u over delta u, which equals 1, provided that delta u is not 0. Now we're looking at a little change in u here. Provided it's not 0, this rule is going to work. Now that is a flaw in this proof. If delta u is 0, we will have a link to another proof of the chain rule. It's a little more involved looking at this one and saying that provided delta u is not 0 is going to make it easier to see where the chain rule comes from. So we're going to do that, and then following this video will be a link to a precise derivation or proof of this without any kind of a stipulation. Now we could express these little changes in x and u. We can just reorder those, and then we have the limit of a product, so we could write that as a product of the two limits. And then in looking at this, we see that this one we don't have a delta x in there specifically, but as we look here, as if our little change in x goes to 0, then our little change in u also goes to 0, so we could express this as the limit as delta u approaches 0 of the change in y over the change in u, and then the limit as delta x approaches 0 of the change in u over the change in x. Well, this is just simply the definition of the derivative dy du, and this one the derivative du dx. So we could express those using Leibniz notation, and let's see essentially what this tells us. So if we have a composition, we have a function within a function, and we're calling this inner function u, it says we need to take the derivative of dy du. So this dy du, here is y as a function of u. This is the outside function, so we would take the derivative of the outside function, which would be a power rule, power out in front, decrease the power by 1, and then we would need to multiply that by the derivative of u with respect to x. Here is our function, and this was the function that was inside, so essentially this is saying then we need to multiply it by the derivative of the function inside. So if we applied the chain rule to this problem, essentially it would tell us that if we want the derivative, we first work with the outside function, move the power out in front, decrease the power by 1. We would not change the u, or the what's inside, so that would stay the same, but then we would need to multiply this by du dx. So we need to multiply this by the derivative of the function that's inside, and the derivative of 5x is 5, and of course the derivative of 4 is 0. So after doing this, in order to simplify this, we could multiply this out. It looks like we have 10 times 5, which is 50x, and then we have this 10 times 4, which is plus 40. So we would arrive at the correct answer. So if we applied this to this particular function, so what we are going to do is work with the outside function. The inside function, which we can think of as u, is 5x plus 4, but the outside function is u to the 100th. So basically we can apply the power rule, which would be power out in front, decrease the power by 1. We don't change the stuff inside here. This is our u. We're just simply working with the outside function. And then we need to multiply that by the derivative of what's inside. And multiplying by the derivative of what's inside here would be multiplying by 5. So we could express this as 500 times the quantity 5x plus 4 to the 99th power. So here is the chain rule, and it's expressed in two different notations. You can see down here at the bottom was the one we derived, the Leibniz notation. Let's read this. If g is differentiable at x and f is differentiable at g of x, then the composition function capital F, which is just f composition g, and it just means that we have g of x inside of the function f, is differentiable at x, and the derivative is given by the product. So the derivative is the derivative of the outside function. You do not change the stuff inside when you do this, and then you multiply it by the derivative of what's inside. So here it is with Leibniz notation, calling the stuff inside u. Here it is, the stuff inside is g of x. This was first formulated by James Gregory, a Scottish mathematician, and you can see by the years he lived that he was working at the time that Isaac Newton was working, and he formalized the chain rule. So let's see this in action. If we want this derivative, we see that we have a function 4 minus 3x inside of a function to the 9th. We could officially identify our u, or we could just kind of say, well, it's the function inside. Y is our function of u, then would be just u to the 9th. I'm writing this out so you can see where the different pieces come from, but as I'm looking at these, typically I say, okay, I have a function inside, and so I'm going to work with the outer function. So this would be a power rule. Power out in front, decrease the power by 1. You do not change the stuff inside when you're working with the derivative of the outside function. This is our g of x, and it remains our g of x. But then we need to multiply by the derivative of g of x. So looking at the derivative here, the derivative of 4 is 0, and the derivative of negative 3x is negative 3. Negative 27 times the quantity 4 minus 3x to the 8th would be the derivative here. Let's look at one more. We learned that the derivative of e to the x was e to the x, but this isn't e to the x. This is actually e to the u. We have our outside function is e to the something, and our inside function is negative 5x. So this is a composition function of e to the negative 5x. So in finding a derivative, I first take the derivative of the outside function. The derivative of e to the u is e to the u, or e to the something is e to the something, so that part doesn't change. But then I need to multiply it by the derivative of the something. The function inside was negative 5x, whose derivative is negative 5. Now this chain rule works when we have more functions inside of functions. So this one is just showing us what if there were 3 functions and we had one inside of another inside of another. So we had y is f of u, but u is g of x, and then x is h of t. And so you would use the chain rule twice, and essentially as you're looking here, you start with the derivative of the outermost function, then you move inside to the next function and multiply by that derivative, and then you move finally to the innermost function, multiply by that derivative. And this would continue to work for however many functions that you had. They call it the chain rule, but I think of it like these nested functions, because you have one function inside of another inside of another. So I picture it more like something like this. You have an outer function and then a function inside of that. We could have a function inside of that, a function inside of that. We could just keep going like this. So looking at this particular example, I've got these functions nested, and we're going to try and identify then the outermost function and then the next function in the next one and so forth. And so the first thing we want to do when we have these trig functions kind of written with this shorthand notation is we're going to want to write them probably, I'm going to put brackets around this and cubed, because it's a lot easier to see what we have here, and we can easily see that the outermost function is a cubed function. So the first thing that I'm going to do, I'm working on this outer function, and it is something cubed. And so I'm going to take the derivative of this whole function by starting with the outermost power rule, power out in front, decrease the power by 1, but I don't change the stuff inside. So this function inside, well, there's functions within functions inside, but none of that changes. I would just, in that step, was doing the power rule on the outermost function. Now, as I look to see what's left, I look to see what was inside, and I identify the outermost function there, and the outermost function there was a cosine function. It was the cosine of some stuff. And so I am going to take the derivative of cosine of something, and the derivative of cosine is negative sine, but the stuff inside, the function in there, does not change. So it's still of e to the negative 2x. Now I'm ready to move inside one more time, and I see that inside I have an e to the something. So the next function is e to the something, and so the derivative of e to the something is e to the something, but we can't forget we're not done. We still have to apply the chain rule to the something. So the very next one, I look to see what was inside of the e function, and we see that that is negative 2x. So we need to take the derivative of negative 2x, and of course that's just negative 2. So there we have it. When we have this composition of functions multiple times, we work with the outermost function, leave all of the stuff inside alone. And then we move in a function, we work with that function, we do not change the function inside. And then we keep moving in until we finally get down to the last function there, which was a negative 2x. Now the last thing to do is we could do a little bit of simplifying. We've got some constants that are multiplied here. We've got a negative 2, a negative, and a 3. So I could express that as a 6. I have an e to the negative 2x, so I'll go ahead and list that next, I guess. And then I have a cosine squared e to the negative 2x, and I have a sine of e to the negative 2x. And the order of those last factors doesn't really matter, but it's probably good to combine your constants. So there is our derivative after multiple applications of the chain rule.